So it's a great pleasure for me to have Carl Bergstrom as our last speaker of our seminar series. He is a professor of biology at the University of Washington and generally interested in many things. He's mainly working on modeling the flow of information through biological and social systems. And he's also concerned with the spread of disinformation on social networks and interested in what can be done. He's known to be the co-author of a book on misinformation called Calling the Bullshit, and teaches a class by the same name at the University of Washington. He's also interested in norms and institutions and how they influence research strategies of academics and how it influences our scientific understanding of the world. All right. And with that, I give it to you, Carl.
Great, thank you very much. It's a pleasure to be here virtually, at least. I apologize I can't be here in person, but thank you very much for obliging me with the opportunity to speak in this way. What I want to do today is talk about high risk, high return research. And so in some ways, this won't be your typical epidemiology talk, but I hope it's at least interesting. And I want to start off by kind of giving a picture of the approach I'm going to take and then tell you about some recent findings that at least I think are provocative for how we think about what it takes to foster high risk, high return research. All of this is work that's done in collaboration with Kevin Gross in the Department of Statistics at North Carolina State. And I want to start by saying, look, science is perhaps the greatest human invention. It is an amazing way of doing things that gives us literal superpowers as human beings who live in a very delimited amount of space and a delimited amount of time. We have evolved sensory apparatus that allow us to detect to detect phenomena on the scale from a few dozen microns to a few dozen miles. We have an understanding in the sensory apparatus it takes to understand the world on time scales from a few milliseconds to a few decades. And yet, what science gives us is these superpowers to be able to understand the world on very, very different scales. We can understand the vast expanse of the universe. We can understand what happened in the femtoseconds after the Big Bang. We can uncover the molecular basis of life and build an entire technology around that. And indeed, one of the things that science does give us is the ability to leverage our understanding of the world to create technologies such as Wi-Fi that works at 30,000 feet, while going 600 miles per hour across the continent, or develop a vaccine to a disease that had never been in humans less than a year before the vaccine was available commercially. It offers a stunningly successful illustration. This is something I've been very interested in lately, is collective intelligence. And so it shows a fantastic way that collective intelligence can be organized through a set of norms and institutions and principles. But the thing is that we sometimes get a little carried away and think of science as the sort of, the ultimate way of understanding the world. And it's not as if we sat down and sort of came up with a priori the mechanisms, rules, and everything else for science. Rather, what we see as science was, inherited largely from a cultural tradition of the way that essentially, wealthy people studied natural philosophy in Western Europe over, 2, 3, 4 centuries ago. The norms and institutions that we have around science are these culturally inherited norms and institutions that themselves are jury-rigged over the sort of evolved psychology of one's particular species of ape, namely ourselves, to allow us to collaborate and do all of this. And so the thing is, if, for example, bees did science, it would likely look very different from what we do. There's an arbitrariness to the entire system of science that could be frightening, but as I'll try to argue, is actually gives us a lot of opportunity to make things better, to improve science as we move forward, and to adapt it to the new kinds of problems that we're facing. So one of the key things that I like to think about, of course, is what motivates scientists. We have this picture, this sort of intuitive picture that's in a lot of our heads where, here's St. Jerome in his study. He's got this sort of divine light of inspiration and curiosity, and he's kind of working away in solitary labor to understand the world and to bring logos to mankind. In reality, this is my colleague Jevin West, and he's doing science, and here it's in part because he's stoked to get a TED Talk, right? And so there's this there are these terms for this distinction that Philip Kitcher has, which I just love. He talks about epistemically pure activity. So these are people that are only interested in pure curiosity, purely understanding the world, and then the rest of us are epistemically sullied in the sense that we are operating within a scheme of incentives, and we have these other motivations other than pure knowledge. And the thing is, every single one of us is epistemically sullied. If anyone were not, they would not do the things they needed to meet the continuation conditions to be able to stay in science. And that's actually probably good, given the way that the norms and institutions of science are set up. The fact that we're epistemically solid, the fact that we respond to these incentives actually is able to drive more productive, more useful scientific activity. At least that's the thesis of Michael Strevens's book, The Knowledge Machine, which I recommend enormously as fantastic exploration of how science works. So in order to understand science, my view is that we have to understand a few things. We have to understand the choices that individual scientists make. We have to understand the incentives that motivate those choices, and we have to understand the institutions that create those incentives. And that sort of combination of questions that we're trying to make sense of constitute what I think represent a research program in understanding the function of science and understanding how we can improve the function of science. So the way I like to think about it is sort of can be captured in a diagram like this. You've got these norms and institutions. These can be brick and mortar institutions like the NIH or universities. They can be institutions like that are sort of conventions, like priority rules for credit, the norms of authorship, things like that. These create incentives for scientists to do certain things. Scientists, being human and being epistemically sullied, as we all are, respond to these incentives when they choose their research strategies, when they choose their publication strategies. Those research strategies are used to query nature. That generates knowledge. And so there's sort of a picture of what's going on. And the thing that's really key to recognize about this picture is there's a very direct connection between these norms and institutions, which of course are these cultural legacies of Western European practices a few centuries ago. There's a direct connection between that and the knowledge that we have, the things that we believe to be true about the world and are correct, the things we believe to be true about the world and are wrong, the things we don't know because we haven't looked at, all of that. And so there is this direct connection between this arbitrary set of norms and institutions, somewhat arbitrary, right? They're constrained and they're themselves subject to an evolutionary process and all of that, and the knowledge that we have about the world. And that may feel, a little bit scary. But what I see is very empowering about that is that as we find our ability to create knowledge about the world falling short of our aspirations, we have the ability to come back and tweak these norms and institutions in ways that can improve that. And as we build up a theory and we build up a full picture of how this process works, I think we may be able to do that with increasing efficiency. One of the things that we've kind of faced up to this point is that different parts of this diagram fall into very different disciplines. The understanding how norms and institutions are, evolve and create incentives is really the domain of the sociology of science. The way the sort of, labor allocation problems and the way that scientists respond to incentives and choosing their research strategies has fallen in an area that I'll call the new economics of science. And this work, looking at how research strategies, and often it's very normative, can lead to knowledge is largely the domain of the philosophy of science. And I feel like these need to come together. And this is one of my major aims, is to establish and perpetuate collaborations among people in these different fields. The work I'm going to talk about today is largely, but not exclusively, in the domain of the new economics of science. So I want to just say a little bit about that. That was a movement that started in the 1990s. There's this sort of key paper by Das Gupta and David that lays out this approach. And what the new economics of science does is basically takes the tools of microeconomics and applies it to thinking about scientific activity, not in the sort of large scale sense of how we fund of the sort of what are the economic rewards to, macroeconomic rewards to investing in science and the spillovers into technology, but rather actually thinking about how these individual, incentives motivate researchers to do things. So the new economics of science typically features, analytic methods in the sort that you'd see in mathematical microeconomics. It borrows on this rich toolkit from theoretical economics, all of these, different mechanisms, if you will, markets, auctions, signals, contests, voting, taxation, while using basic domains, decision theory, public choice, game theory, mechanism design, and focuses on a sort of key set of ideas, equilibrium notions, typically notions of strategic choice on the part of individuals. So you've got, individuals' choices depend on the choices of others. It's very much rooted on information economics. There's a lot of focus on how uncertainty is managed, and being, mathematical economics, there is an emphasis on the efficiency or lack thereof of the outcomes that emerge from individual behaviors. So that's sort of a domain of research into how science functions, and that's the one in which what I'm going to do is situated. In this area, we can of course use simple models to illuminate, and this is again very much in line with what we see in mathematical microeconomics, to illuminate the key processes in a bunch of different domains. How peer review works, norms of partial results, publication bias, how grant funding works, all of this. And from these simple models, we can derive intuitions about how the institutions that drive science function. And it provides, again, coming back to this notion of collective behavior, it's sort of a fantastic model system for studying the organization of complex cognitive effort. Once we make some progress with this, it offers the possibility of rational design of institutions. If we have a theoretical foundation for thinking about how institutions create incentives, and those incentives drive activity, and that leads to knowledge, we have the potential of being able to shape our institutions in ways that create better understandings of the world through the downstream processes of influence on scientific activity. And I think that holds a lot of promise, and it's where I'm putting a lot of my research activity these days. What I want to talk about today, so that's sort of an introduction that gives you sort of the framework in which I'm going to be thinking. What I want to talk about today is about high risk and high return research. So first of all, what do we mean by risk? I think people, when they talk about high risk research, they may refer to a lot of different things. In some cases, people are talking about research projects that simply have a high probability of failure. They have a high probability of you do the project, it just simply doesn't work. You're chasing after, hey, is this the explanation? Is this a mechanism? Is this a possible treatment? And the answer is no. In some cases, when people are talking about high risk research, they're talking about research that goes against the grain of current thoughts. Somebody's got an alternative viewpoint and is trying to buck current trends, trying to demonstrate that a current approach is a current theoretical framework is not adequate. It may be working in brand new areas that are so new we don't even know how to evaluate possible outcomes in those domains. Whatever high risk research is, it's pretty clear that people tend to think we don't have enough of it. So if you ask people about this, whether you're talking to scientists, whether you're talking to program administrators, program officers, people tend to think that science doesn't support enough high risk, high research, high reward research. And there are plenty of surveys and things like that that provide some support for that. Here's a survey that was part of that came out of the FAST Grants program. Leaving aside your COVID work, how would unconstrained permanent funding change your regular research program. So you same amount of funding, but you can just do whatever you want with it. The vast majority of researchers, nearly 80%, say they'd change their research program a lot, and pretty much everyone else says they'd change it a little. So it suggests that the sort of constraints of the funding process are limiting people's ability to do what they want to. There's also a lot of work suggesting that research is in a sense too conservative. This is a beautiful study, one of the best in this area that I've seen, by Jacob Foster and his colleagues. And what they did was they looked at sort of the network of interactions among chemical compounds, and they found that most of the activity in chemistry in this sense was basically consists of triangle completion. You take two chemical compounds, A interacts with B interacts with C, and then you show an AC interaction of some sort and work there. So they say, the vast majority of effort is either working on cases, people already know about interactions between A and A, and A and B, and so then you work on that some more. This is sort of triangle completion stuff. There's much less if you take this network of chemical interactions. There are far fewer papers that make big jumps in that network and connect two things that were at quite different places in the network. But the papers that do that garner the vast majority of the citation. So they garner the vast majority of awards in biomedicine. They garner the vast majority of awards in chemistry. So what they concluded from this paper, and I won't go into this in detail, was that very early on, the sort of strategies of just linking nearest neighbors and things like this may be sensible. But at this point, where chemistry and biochemistry are well-developed, mature fields, there's way too little of this sort of riskier research and way too much sort of conservative research. In other words, it's, if you think about an exploration-exploitation trade-off, there's way too much exploitation and not nearly enough exploration. This is talking about sort of misunderstandings of high risk, high return research. Here's the ERC explaining that their high risk research program was extremely successful because 80% of it achieved major scientific advances. Now, that's a very successful funding program, but it is not a high-risk one. If you're getting 80% of your funded projects are doing major advances, it's a very conservative one, albeit possibly a successful conservative one. So, so then for experienced researchers, 99% of their high-risk grants made appreciable scientific contributions. Again, absolutely not high risk. So for some reason, high risk research, if important, is not getting funded. And then you can ask people, well, why is that? Why don't high risk proposals get funded? Why don't researchers do high risk research? And you get two different answers. You ask the researchers, they say, well, the funding agencies won't fund it. And you ask the agencies, and they say, well, the researchers won't propose it. And what I want to talk about today is a pair of papers that take the perspective of each of these two ravens, so to speak. And I'll start out with the funding agencies won't fund it piece. This was published a couple of years ago in PNAS. And then I will more concisely tell you a little bit about the researchers won't propose it piece that's currently a paper on the archive. So in order to think about why funding agencies won't fund it, it's helpful to think about the notion of filters in science. In order to go from an idea to having sort of influence in the scientific community, you have to go through this whole set of filters. You start out with this idea and you ask, well, shall I propose this? And if so, you sort of write a grant proposal, and then the funding body says, shall I fund it? And if so, the experiments take place. And then if those are successful, you think, well, shall I write this? Or after you do that, you think, well, shall I write these up? And if so, then you have this manuscript and you send that off, and the journal peer reviewers just decide, shall we publish this? And then maybe it makes it to publication, and then people think, well, shall I read this? And then once they've read it, they think, well, shall I cite it? And then finally, we've got citations. So there's this whole set of filters that these ideas have to go through. And I want to focus in particular today on two of these filters, in particular, the two peer review filters in this diagram here. They are the ones leading from proposals to experiments. So this is grant peer review. And then they're the one leading from a manuscript to a publication. This is journal peer review. And the key thing that I want to stress here is that the former of these, this funding decision is made ex ante. It's made before the results of the experiments are known. You've put in this proposal, you say, I want to do these experiments. We'll see what happens. Whereas the journal peer review process is done ex post. The results are in, you've got them there in hand, and now you're trying to make the argument that the paper is worth published. And I'm going to argue that that ex ante and ex post peer review favor different kinds of science and leave the investigator in the position of trying to navigate a tension between these two types of review. Ex post review, as I'm going to argue in a moment, it allows investigators to leverage their private beliefs about the way the world works. This could be things they know from a lifetime of experience in working with a particular study system. It can be from unpublished preliminary data. It can be hunches. Any of those things ex ante review does not. And we'll talk about that. We'll come back and sort of summarize with this slide again shortly. To get there, though, I want to start thinking about what's the value of doing an experiment. So you say, well, I've got this experiment I'm going to do. I don't, this is kind of basic decision theory. I don't know what the outcome is going to be. But I've got some set of beliefs about the probabilities of different outcomes and their values of different outcomes. So we can kind of think that, what experiments are worth doing? Well, they're ones that somehow have this high expected value, high probabilities of high value outcomes. And if you talk to funding agencies or talk to journals, everybody wants to support useful research. Funding agencies say they want to fund it. The journals want to publish it because that's what's going to attract readers, and it's going to lead to increases in citations and lead to increases in impact factor and all that. But what defines useful? What I want to argue, and one of the major contributions of the PNAS paper, I think, is that we've come up with a very rigorous formal argument for this, is that a scientific result is useful to the degree that it changes beliefs about some epistemic object, a hypothesis, a model, a claim, a parameter value, whatever it is. And by changes beliefs, I don't mean that it flips your belief from, say, oh, I think this is false to I think this is true. It may just increase your confidence or in something, or cause you to or further decrease your confidence in something you already thought was unlikely. But it moves your beliefs around somewhat. And the informal justification for this is if you do a study and it doesn't change anyone's beliefs about anything, what was the point in you doing it? If there's a paper that's not going to change my beliefs about anything, what was the point of me reading it? And again, a paper that makes me more certain of something I already thought was likely is quite useful to read, but that has changed my beliefs. It's made me more certain about something. A paper that's, where I thought something was 75% likely. I read the paper and I'm still in the same place afterwards. Very little point in me having read that paper at all. So that's sort of the informal justification. In the PNAS paper, and for people who are interested in these kinds of decision theory things, we're actually able to ground this. And so that claim about how the value of an experiment is proportional to the degree to which it changes beliefs has sort of been a core piece of a lot of work in the philosophy of science, but has lacked a formal mathematical foundation from decision theory up till now. And so, so we were able to sort of fill that in. The approach that we take, and you can read the mathematical proofs in the paper if you're interested. You take any decision problem, and we can show that you take a decision problem, take a Bayesian updater, and you say the more the Bayesian updater changes their beliefs based on new information, the better they expect to perform at the decision problem. So the Bayesian updater will believe that the information that they have just received is useful to them in proportion to the degree to which they change their beliefs based on that information. And you can prove that very broadly and prove it for a very broad, and so not just for any decision problem that they face, not just understanding things, but even very instrumental decision problems. I'm not going to go through any of that mathematics because that's a little tedious for those who are not interested in such things. but you can find it in the paper. Instead, I want to sort of continue to try to build some intuition about these ex ante and ex post peer review processes. So we've said that the value of an experiment, under this framework, was equal to the probability of the outcome times, and we were saying the value of the outcome. And now I'm arguing that, well, the value of an experiment is proportional to the probability of outcome times, what's the value of an outcome? It's how far the beliefs shift, right? So it's the value of the resulting belief shift. So we then add, the value of a belief shift is the amount by which a Bayesian updater perceives that their forecasts of empirical phenomena have improved. This is just taking kind of a constructive empiricist view of scientific activity, which I think of as sort of a very lightweight framework for thinking about what science does. It may do a lot more, but the constructive empiricist view just simply says, scientific activity is aimed toward making, drives us toward making empirically adequate models of phenomena in the world. And then we can argue, people can take much stronger views of what science is and so on, but very few people would argue with the fact that it does at least that much. So this is sort of the value of a belief shift. And then what we have to ask ourselves as we think about measuring the value of an experiment, well, whose beliefs are we talking about here? So you're talking about the value of a belief shift. Are we talking about are we talking about the value to the investigator? Are we talking about the value to members of the community, and so on? And we also have to think about, and I should come back and stress this, we also have to think about whose probabilities do we use here? Say, well, the probability of an outcome, are we talking about what the investigator thinks is likely to happen? Are we talking about what an outside reviewer thinks is likely to happen? And depending on what we fill in there, we may see very different sorts of, we may value an experiment in very different ways. So we can make a little table, say, whose beliefs do we use to anticipate what's likely to happen? Do we look at what the investigator thinks will happen? Do we look at what a reviewer thinks will happen? Do we look at what the whose beliefs will shift after observing the outcome? Do we think that the the investigator's own beliefs will shift, that the reviewer's own beliefs will shift, or do we think that everyone else's beliefs will shift, that is not the investigator, or everyone else, not the reviewer's beliefs will shift? And each of these kind of lead us to different valuations. In the case where we can kind of write these out as well in terms of the types of peer review that we're thinking about, right? So if we have an investigator who uses her own beliefs to anticipate the likely outcomes, and she's interested in only how her own beliefs shift, this is someone who's just doing epistemically pure science. She's just trying to figure out, she's trying to understand the world as best as possible, not worried about the rest of the scientific community, and just wants to find the thing that she thinks, oh, excuse me, that went forward. She wants to just find the experiments that she thinks will tell her the most about the world. That is not typically what gets us through peer review. If instead an investigator uses her own beliefs about what is likely to happen and looks at how much they'll change other people's beliefs, that's sort of the dilemma that an investigator is dealing with when facing ex post peer review. So the idea is, I'm trying to come up with an experiment that I think is most likely to generate results that other people are going to find most surprising. So they're going to move other people's beliefs a lot. I'm going to use my own beliefs in sort of evaluating these probabilities, because I'm going to have those results in hand when I mail them off to the journal, or hit send these days, and then they will be evaluated by people who have the results in hand, and they'll sort of know how much their beliefs will shift because they're reviewing ex post, and then they'll say, oh, if their beliefs shift a lot, they'll say, oh, this is great, this can go into Nature or JAMA or whatever. If I instead submit a paper for ex ante peer review, now you have a situation where where we're using the reviewer's beliefs to anticipate the outcomes. I have this private knowledge about what I expect to happen. I send this off to the grant panel. The reviewers have their own beliefs about what's going to happen, and so they may say, okay, I'm going to, do I think this experiment is going to work? No, I don't think this experiment's going to work, because their beliefs may be different than mine are, and so they don't think they'll learn anything. Or maybe they say, I don't think this experiment's going to work, and then they can look at what everyone else might learn. And we'll talk about the distinction between these two momentarily. But the basic idea is that I'm trying to highlight here is this distinction between ex post and ex ante peer review. And so we can kind of where ex post, you have the results in hand. You as the investigator use your own beliefs to try to pick a project that's going to generate something surprising to everybody else. When you're doing ex ante peer review, like a grant, you've got to write a grant proposal where other people will believe it's going to generate a result that's at least reasonably interesting to them. And so in order to try to get a sense of I mean, so you can, of course, write out this mathematical model. You can do all of this analytically. We also wanted to kind of understand how, for sort of reasonable distributions of scientific beliefs across the scientific community, about what project selection might look like. And so we kind of did a simulation of this. You could look, but basically I've got two axes here. So you have an investigator who has a favored claim. So there's a claim that the investigator thinks is likely to be true and generate positive results. And now we want to say, so imagine that the investigator has to choose from a bunch of different possible research topics. Each of these, the investigator thinks is likely to actually work. And then what the investigator is trying to do is of those research topics, the investigator knows what is the community's belief in those topics, how likely does the community think that is going to be to work, and then how homogeneous or heterogeneous is the community in their beliefs about this question. So you might have, and so here we've sort of simulated, a set of community beliefs, and then what we do in each of these circles is the best choice of a research project from a set of projects given a set of community beliefs. So the theoretical optimal thing to do, if you could find a project like this, would be to work on something that the community thinks, that the community is united, so there's low disagreement among the community. The community is united in thinking is fairly unlikely to work. You don't want the community to think it's super unlikely to work, because then even if it does work, they won't believe your result. You want this sort of, low but not near zero certainty on the part of the community. If you're going through ex post review, if you're going to send a paper to Nature, the best thing to do is send something where everybody thinks it probably wasn't going to work, but they can believe it once it comes in. Whoops, sorry, that just shifted forward. Let me fix that. There we are. In practice, it's hard to find projects like that. And so in our various simulations of sort of distributions of beliefs, the projects that investigators end up choosing are illustrated by these circles here. So they tend to be projects where the community thinks that there's a less than 50-50 chance it's going to work. There tends to be some disagreement in the community, and that's mostly because we have to have a situation. If there's not some disagreement in the community, it's really unlikely that the investigator thinks one thing and everybody else thinks something different. So that's what happens when you're facing ex post peer review. When you're facing ex ante peer review, so ex post peer review, right? And I guess this is sort of the takeaway from this. Ex post peer review rewards researchers for exploring hypotheses that they think are likely to be true, but the community considers unlikely. Ex ante peer review is a bit different. So if you send something off to a grant panel, the reviewers then use their own beliefs, and they look at how much the results will affect their own move their own beliefs should they happen. So then the best thing to do is to pick something that the entire community agrees is a 50-50 proposition. And the reason is because these reviewers, if the reviewers can't expect to be surprised themselves, right? Bayesians can't expect to be surprised themselves. So the most a reviewer can possibly expect to learn is in a 50-50 proposition. And then if they're looking at their own changes in beliefs, then if everybody agrees that it's about a 50-50 proposition, then their own beliefs are likely to also be, that it's a 50-50 proposition. And so that's sort of what we see there. If instead, okay, so I guess that's the second takeaway. The ex-ante review doesn't give the researchers any way to leverage their private beliefs. They have to study things that the reviewers think are going to be interesting ex ante. If I think something will work and the rest of the community doesn't, there's no way to sort of leverage that, because if I send that in for grant review, then people will say, oh, that won't work. It's not worth doing. I have to send in something where everyone agrees that this could kind of go either way and would be interesting. And that really sort of hamstrings my ability to pursue what I think is the most interesting, most promising directions. If ex-ante reviewers focus on how much they're going to be surprised themselves in their own, how much the results will move their own probabilities, they're going to favor resolving shared uncertainties. That was what I was just talking about. They're going to favor resolving these cases where everyone agrees it's a 50-50 proposition. Something pretty different happens if they look at how much they expect it to change other people's beliefs in the community. Then the best thing to do is to propose a project that's going to resolve an issue where there is a lot of heterogeneity in the community about what people believe. You want the community on average to be about 50-50. So what you see right down here, we have, sort of a shared uncertainty about what's going to happen in the world. Up here, we have a scientific controversy. The average belief of the community is that it could go either way, but there's a lot of heterogeneity, which means there's a lot of people that are sure it's going to go one way. A lot of people are sure it's going to go the other way. So if reviewers pay attention to how much am I going to learn from this experiment personally, they're not, in this case of shared uncertainty, everybody thinks they already know what's going to happen. So they think I'm not going to learn much. So if you had a sort of a controversy, the shared uncertainty, they think, oh, I don't know, no, so I'll learn from this. In the case of a scientific controversy, I say, well, look, I know what's going to happen. Whoops, sorry, I apologize for this slides. I say, I know what's going to happen in this experiment as a reviewer, but those guys at Stanford don't realize that it's going to go the way I think instead of the way they think. And the guys at Stanford say, well, I know what's going to happen, and Carl doesn't realize it's going to go the way we think, not the way he thinks. And so what if reviewers are told to if they're asked how informative is this going to be to you, they'll favor these shared uncertainties. If they say, how informative is this going to be to the field, they'll favor resolving these scientific controversies, which are, of course, very different things. So if ex-ante reviewers focus on how much an experiment changes the views of others, they're going to favor resolving scientific controversies. One thing that we note is that so this is sort of coming back to this slide I promised to, we see ex post, ex ante review encourage different kinds of science. Ex post review allows investigators to leverage these private beliefs, unlike ex ante review. And the ex ante review criteria, we notice, are often subtly ambiguous. So when you go to a grant panel, you're often, I've never been told, hey, evaluate this based on how much you think you'll learn from it versus how much you think the community will learn from it. And by sharpening those distinctions, we could, funding bodies could aid the reviewers in selecting proposals that did what they wanted to, either address shared uncertainties or address scientific controversies and so forth. And one good way to sort of do that, it's often hard to know what other people believe, and so one possible advantage of a grant panel would be to pull people together. I read a proposal, I score it thinking, oh, this isn't going to work. This experiment is no good. This experiment is a total waste of time. Then I get there to the grant panel. Someone else says, oh, yeah, this experiment was obviously going to work. And so I think it's a waste of time. And then all of a sudden I realize, wow, we've got a disagreement here. And this experiment's probably worth doing after all. So this is one reason why it might actually be quite useful to sit people down and do grant panels and things. So, an sort of implication of this, right, coming back to the risk issue, is that when grants are reviewed ex ante, researchers can't afford to submit risky grant proposals, in the sense that they can't afford to submit proposals that sort of go against the grain of what people believe, because the reviewers will expect them to fail. That's not true with submitting papers to Nature. You submit a paper to Nature that goes against the grain, you've got the data there. They already know it hasn't failed, right? And so one thing to keep in mind is that other modes of ex ante review, such as registered reports, may similarly discourage risky work. Registered reports may be very useful in many cases, but I'd hate to see them become ubiquitous, precisely because then we would have to we'd have to propose experiments that that the reviewers would expect to work, or else we couldn't publish them. We wouldn't be able to follow our own hunches, get the results, and then take them to review at that point. So I want to just comment briefly on one more thing here before we move on to the second part, which is which will be much briefer, which has to do with what is known as the demand for non-instrumental information. It's based on a really important economics paper about suspense and surprise. And they define suspense essentially as a change in what we know. A surprise is a change in what we know, and suspense is a sense that what we know is about to be changed. We're in a situation that's propitious for getting information that's going to change what we know. Note, this is a quote from the paper, note that suspense is experienced ex ante, whereas surprise is experienced ex post. So when we write a grant, we aim to create suspense. We aim to create the feeling that this grant is going to lead to outcomes that are going to change people's beliefs. When we write papers, we aim to create surprise. And we, in the sense that we actually, this is being reviewed ex post, so we want to create surprise. And this is, I think, helps explain why we do something that I don't really see in other areas. Imagine that I had a, I was reviewing the, the latest book from Stephen King or something, and I said, okay, here's my review. Here's all the reasons why I think this latest Stephen King book was going to suck. And then, oh, but actually it didn't suck, and blah, blah, blah. And you don't read book reviews like that. But sort of every scientific paper you read is like, here's all the reasons why you wouldn't expect this, but we found it anyway. And what are we doing there? Well, essentially, we're trying to convince the readers, and the referees in particular, that we're trying to create sort of a sense, trying to create convince them that they have been surprised, or at least they should have been surprised by the findings of our paper. And we convince them that either their probabilities have been moved substantially, or that any sensible reader who knew all the things we put into the introduction would have their probabilities moved by our findings. Okay, the last 5 minutes or so, I want to just very briefly outline an argument on the other side of the question. So the researchers say the funding agencies won't fund it. I've argued that it has to do with the difference between ex ante and ex post research. Funding agencies say researchers won't propose risky research. Well, why not? We've got another paper that's currently on the archive. You can take a look at that, Rationalizing Risk Aversion in Science. And this paper lays out economic argument for why people don't propose risky research very often, independent of the fact that it is unlikely to get funded, even if they do. And it starts with this fact about how scientific reward systems work. As scientists, we're rewarded for our output, right? The prestige that we get, the promotions we get, hiring, all that. None of it's based on someone saying like, wow, that guy sure worked a lot of hours last year. It's all based on, how many papers did you get? How influential were they? What grant funding did you get, et cetera? And the classic argument for this, at least, and we can argue about whether this is right or wrong, but the classic argument for this is that it's virtually impossible to monitor a scientist's effort. You can't just watch them, what they're doing. And so therefore we have to be rewarded for output. That ends up shaping a lot of the way that scientific incentives and institutions work. So we're rewarded for this output. But of course, like anybody, or most people, these scientists are risk averse in wages, where by wages, I mean all of the things scientists care about: their monetary compensation, their job security, the sort of prestige they have within the community, all of that. So scientists are risk averse in that. And then there's this dilemma when you think about what a funding agency can do. Imagine a grant panel or a charitable foundation. They can hedge across a portfolio of grants. They could be sort of like a venture capitalist and set up this set up a venture fund or set up a grant a set of holdings of grants. Maybe they fund 20 grants, and if they get two big hits, that's going to completely justify their existence, and the grant manager is going to come off looking really good. Individual researchers can't do this because, of course, we've only got time to run one or two major research projects. I'm thinking of sort of a mid-career researcher running on a couple of R01s or something like that, right? And so you can't hedge across a whole portfolio of grants. You can't, if you've got a couple of R01s and both of those R01s end up being dead ends, you've got big problems, right? You're going to have to you're going to have a gap in publications. You're going to have a hard time getting your next grant. You're going to have to lay people off, all of this. So there's an ability of these funding agencies to hedge in a way that individual researchers can't. What you might normally do in this case is say, well, okay, that's fine. We want individual researchers doing risky research. So we're going to insure them against failure. We're going to say it doesn't matter whether your two R01s fail or not. Because we want to make sure that you feel free to go after riskier things. But if we did that, this comes back to there's this. Remember, we can't monitor effort, and so if you were to reward people, even if they came up with no output at all, then they could just loaf all the time. So you can't distinguish in science. If you can't monitor effort, you can't distinguish bad luck from loafing. And so this puts us in this bind where the measures that we need to incentivize effort to keep people from loafing, namely rewarding people only for their output, ends up discouraging people from taking adequate risks because they're risk averse. They don't want to. They can't hedge across a large number of portfolio. They can't set up a portfolio with a large number of research programs in it, and so because they have to be able to come up with some output. They are going to be discouraged from taking enough risks. Now, kind of looking at, and this is the mathematics that's all in the paper. If you sort of think about how to economic systems get around this, you say, well, if you had a social planner, the social planner might induce optimal effort and risk levels by providing really large bonuses for major results. So if you got a major substantial result, you'd get a sort of C-suite kind of pay raise and that sort of thing. That would cause scientists, even though they're risk averse, they would still gamble some because the payoff of getting a big prize would be so high that they'd be willing to gamble. But when that happened, you'd have a bunch of people gambling and failing. They would suffer. The people who gambled and succeeded, they're risk averse. In other words, they have decreasing utility in wages. So that sort of a lot of the wages would end up going to providing sort of marginal perks to the people that were getting the very most. And this choice that the social planner made while inducing optimal levels of effort and risk would leave scientists as a community worse off. The thing about science, though, is there is no social planner. There's no central external social planner. We have shared governance, and it's not really necessarily because anybody believes in the sort of anybody in the administration believes in sort of the things that we believe in when we talk about the importance of shared governments. But I think it's really because there's a fundamental information asymmetry where the people in high enough administrative positions to allocate these wages don't know enough to know who they should go to. So my dean is a historian. The dean has no idea whether the work I'm doing is good or not. My chair is a neurobiologist. My chair doesn't even know whether the work I'm doing is good or not. And so we end up as scientists in a situation where we ourselves sort of set the wage schedule. We decide what work is worthwhile. There is no external social planner. And what we prove in this paper is that when there's no external social planner, when the scientists themselves get to choose the wage scheme, they're going to choose a wage scheme that leaves them best off. That's going to be a wage scheme that results in below optimal risk taking because they're trading off the need to provide incentives for working instead of loafing, and the deleterious effect that has on risk. And so they're going to end up choosing a sort of a wage scheme or reward scheme that leaves people taking less risk than would most quickly advance science. And the key thing here, and now I'm just finishing up, the key thing here is that in this case, this fact that that the incentive structure does not adequately incentivize risk, it's not just a matter of poor institutional design. It's not just that the institutions we have are bad. It's a inexorable bind that arises from the fact that we can't observe effort. If we really can't observe scientists' effort and we have to reward output, we are stuck in this mess. And so there's not some particular, we can't just simply say, oh yeah, the incentives are wrong, we're going to tweak them, because there's no tweak that would fix them. And I think this is very important to understand as we go to try to solve problems. Which ones are intractable? Where do the problems begin? Which ones, can we sort of tweak the incentives or tweak the judgment criteria or something like that, and are likely to make progress. And so this sort of motivates what I would call, a call for a movement toward rational theory-based science policy, instead of having people making sort of gut decisions without really knowing what impact their new policies are going to have on scientists' decisions, let alone what impact those scientists' decisions are going to have on the creation of knowledge. We can move toward developing the mathematical theory that fills out this whole picture, and we can understand how, once we know what we need to do here, we can understand what changes over here are necessary to implement that, and when productive change is indeed possible. So with that, thank you very much for your time and attention, and I believe I have a couple of minutes for questions.
All right, now we can start with taking questions from the room. Anyone who has some? Otherwise, there's also a question on Zoom. How can you hear me?
I can hear you, yes.
Okay. Yeah, there was one question on Zoom. What would you recommend to a researcher in a project where a grant is already given for the researcher was part of the project to push the existing limits of what can be done in the lab, to pursue or at least create room to start pursuing concepts or ideas they think might be very fruitful?
Yeah, I mean, I think, one of the things that we see happening a lot is we see, so I've kind of laid out these problems around what happens when you submit a risky proposal to ex ante review, and then also these hedging problems, there are inability to hedge across multiple projects. And I think a lot of the sort of standard practices that people tend to do in sort of managing their grants and projects over time actually are attempts as researchers to resolve these dilemmas as best as possible. So one thing that's really common, of course, is that when you're doing ex ante, when you're submitting a proposal for ex ante review, we submit a lot of preliminary data, and we do that, I think, in part to convert that review from ex ante, which we know we're not going to be successful in. We've found something surprising. We know the reviewers aren't going to believe that would happen we believe something surprising will happen. We know the reviewers aren't going to believe that if we just suggest it. So we try to sneak in enough data about, preliminary data, that the reviewer's decision actually becomes effectively ex post. You say, you've got some mechanism that nobody would have thought likely. You think it's worth pursuing. You're never going to get funding if you just say that. But if you come up with adequate preliminary data that the grant peer review becomes effectively ex post, and then you say, okay, here are the preliminary data. And then you've got to, of course, come up with something that you're going to actually do for the grant. But as the other thing people do a lot of, right, is they sort of, they do all the work, and then they write a grant to do that work, and then they use the money they get to do the next set of work, and all of that. And this seems to be sort of a mechanism that people use to get around that ex post ex ante review problem. Similar mechanisms also seem to be used to get around some of this risk issue, where people will run side projects out of sort of existing grants. So you take an existing R01, and you of course don't have to do one single thing on it. You can use some fraction of that R01 to chase a risky hypothesis. So right now, I think way that most of us manage all of this is with some flexibility by sort of being somewhat flexible in the way that we relate what we propose to do in a grant to what we actually do with the grant, which, is not necessarily ideal for anybody, but I think, so I don't mean that necessarily as normative advice, but rather as a sort of descriptive answer to your question.
Yeah, there are two questions from you.
If I speak clearly here, can you hear me?
Absolutely.
Awesome. I was wondering, what do you think about the role of prestige of the scientists themselves in how risky a proposal can be? Do you think that for the more prestigious scientists who are perhaps tenured out of university or have more publications already are easier able to propose more high risk research, or do you think they have a responsibility to do so?
They may have some responsibility to do so. What I'd really like to see, of course, would be the incentives become aligned properly. So I mean, I feel like what the most important thing, rather than saying that anybody has a responsibility to act against their incentives, I want to see the institutions change so the incentives are aligned. That said, and so it's very interesting. I mean, you would think that more established researchers with more job security would be better able to do riskier research, and I definitely see that, with people's changes in research programs after tenure. I didn't think I cared much about tenure, but actually then when I got it, I started doing something that was completely unrelated to anything I'd ever done before that has, since been far and away the most influential work of my career. So I think, yeah, I mean, tenure definitely frees people up to do those kinds of things. At the same time, it's interesting to think about the range of incentives that people face. So a more senior researcher that's running a major lab often feels very responsible for a large number of personnel in that lab. And as a result is maybe at least as risk averse as a junior person who's starting up a new lab. And then I had a conversation that was fascinating once with a graduate student. And I told him, I said, hey, look, he wanted to do this risky project. And I said, hey, look, I'm all in on this risky project, but I want you to understand that your incentives and my incentives might not be aligned. I've got, 5 graduate students. They're all doing different things. If 2 of them succeed, I'm doing great. So whereas you've got one project, and if it doesn't succeed, you've got real problems. So I said, I've got more risk tolerance than you do. And he said, no, you got that backwards. He said, I'm trying to get a job at an R1 school. I know the only way that I'm going to get a job at an R1 school is by having a huge hit. And so I have to take big risks. I've got more risk tolerance than you. So I think it's interesting and to think about, where risk tolerance is highest. And, I'd like to figure out, find a collaboration to do some empirical work on that, both talking to people, but then finding ways to measure what they're actually doing.
Hi, Carl. It's Bill. That was really interesting. I was wondering if you have any thoughts on what would be a rational behavior if one wanted to become, I don't know, the most highly cited biomedical scientist in the world. Would it be to do a large amount of not particularly risky work at high volume that told people things they wanted to know or felt they know already, and would then get a lot of citations from that? Just asking for a friend.
It's very, very hard not to link that question to individual personalities, Bill.
Wow.
I think the citation game is almost a separate game from the risk game. I mean, I think there's I think the most efficient thing to do there would be to understand what people like to cite and the sort of lazy way that people cite, and understand that citation is only loosely correlated with how far you drive science forward, and then optimize along that axis.
All right, there's one more question from Elisa Polinsky. She's raising her hand. I don't know if you can unmute yourself on that side.
Oh, for sure. Thanks so much for a really interesting talk. I have 2 kind of related questions, but I know people are probably running out, so feel free to pick whatever feels interesting. My first is, I was trying to think a lot about what is like the empirical margin for these kinds of decisions. So I was curious if you have a back pocket empirical decision or empirical example that you go to of like a bad marginal decision of where project A was funded, project B was not, but from a societal perspective, you think the reverse would have been better. And then relatedly, a lot of this seems to depend a lot on what the actual empirical value distribution is across different projects. Like we probably don't want to fund the very riskiest work. And if there's a lot of work that has a pretty high probability of having a decent amount of value, it's not clear how far in the direction we would want to necessarily go of things that have a very high risk of having basically no value. And so I was curious if you thought at all about quantifying that empirical distribution or what you think that empirical distribution looks like.
Yeah, I mean, this is right. So these are fantastic questions. Quick answer: I don't have a back pocket example in biomedicine. I have a few in physics that I think about sometimes, but I'm thinking about this. I think more generally there in terms of quantifying all of this. It's very important to do that. I think the most important thing that your question brings up is that I do not have evidence that we are funding too little risky research. I only have evidence that people believe that. And so I actually, you may have noticed, I said, whatever it is, people think we don't have enough of it, not whatever it is, we don't have enough of it. So one of the things that I would really like to do is figure out how to establish whether that's true, that we do or don't have enough of it. The Reshetsky, Jacob Foster's paper with Andrei Reshetsky and James Evans does provide some evidence that we're not doing enough risky research. So one could use methods like that. I've been interested in talking to people about trying to gather ex ante and ex post belief distributions from researchers in various studies. I was interested in doing that across one antagonistic collaboration that had been funded, ended up deciding not to pursue that. But I think what we need to really do there is do a better job of measuring people's beliefs before and after research projects are conducted. So that might involve measuring the beliefs of people on a funding program, then looking at what was funded, and then asking them to assess the outputs of that funding, and then talking to them about their beliefs again afterwards. I'm not an empirical person, and so I need to set up the right collaborations to do this, because I think it's really a key piece of the whole project. And so I don't have a sharper answer for you than that.
Thanks so much.
Thank you very much. Thank you, everyone. Again, I apologize that I'm not there in person, and thank you so much for joining me online.
Well, thank you, Carl, for this very interesting and thought-provoking talk. And yeah, thank you everyone for joining.